So Qian Yu is here, and she is going to present on sustainable fabrication of metal organic frameworks via ball milling, the pathway for improved hydrogen storage. So Qian, you have 8 minutes. No questions.
Okay.
So you can take the whole time for your presentation. You can start now. Yeah.
Okay, thank you. Hi everyone, good afternoon. I'm Qian Yu. I'm supervised by Dr. Mi Tian. Today, I'm going to briefly introduce my research project about the sustainable fabrication of metal organic frameworks for one-pole ball milling for improved hydrogen storage. The metal organic framework I choose for my research is copper BTC. There are normally two typical methods to synthesize the copper BTC. The first one is the thermal synthesis. This is also a very traditional synthesis method. In this method, heat radiation or microwave radiation or ultrasonic radiation will be provided to promote the synthesis of copper BTC from copper nitrate and HBDC. In this method, the copper BTC crystal will be obtained very perfect and large. So this sample will be used in my benchmark in my research. However, in this method, they have some problems. For example, they require a longer reaction time and they need a lot of solvent to promote the synthesis. So as a result, it will cause the energy waste, solvent waste. In order to solve these two problems, in my research, we explore the mechanical synthesis of copper BTC. In this method, the energy will be provided by the crush between the materials and the ball milling and the milling jar. In this method, we only need maybe 1 minute or 3 minutes. We can get the copper BTC, and we don't need to use the solvent to promote the synthesis. So it will solve the problems that exist in the thermal synthesis. However, in this method, we also have some parameters we need to solve. For example, there are a lot of reaction parameters in this method that will influence the property of the copper BTC. In my research, I used the design of experiments methodology to generate 19 experiments to explore the influence of the 6 parameters on the property of copper BTC of specific surface area, crystal size, and yield. The 6 parameters is including rotational speed, milling time, standing time, ball weight, starting materials, and the solvents. Then the design of experiment give me the results that the 6 parameters don't have too much influence on the specific surface area, and it have opposite influence on the crystal size and yield. As there's not too much room to improve the yield, we choose the crystal size as the object to improve its hydrogen storage performance. In a design of experiment crystal results, we can find the rotational speed, starting material weight, and DMS amount will largely influence the crystal size of the copper BTC. As shown in the critical regulation model, when the starting materials weight is 7.2, DMSO amount is 0.1 mil, rotational speed is 280. We can get the largest crystal size at the range of 49 and 56. Based on these results, we get the copper BTC with the largest crystal size to the hydrogen storage. As you can see, we choose 3 samples from the ball milling from the DOE results. The first one is this one. It has the highest crystal size, and then is the capability FF1 is the centimeter of doing the synthesis, and this one, the capability FF14, this has the smallest crystal size. In addition, we also include the capability get from the subthermal synthesis. This is regarded as the benchmark in our research. As you can see from these two figures, the capability with the largest crystal size exhibit the comparable hydrogen uptake to the capability from subthermal synthesis, and it's higher than the capability with smaller crystal size. This result is also the same as the hydrogen absorption kinetic rates. In other words, the capability with the largest crystal size shows higher absorption rate than the capability with smaller crystal size, which means this sample synthesis with reduced energy and reduced solvent can exhibit the higher hydrogen storage, has promising implications. In addition, we also do the characterization of our sample with synthesis from the chemical synthesis. We do the 19th experiment from generated by the DOE and the actual 6 experiments, and then we found out the formation of the capability is through the intermediate phase. This is also valid as the SEM images and XRD patterns. As you can see, this is the intermediate phase. As also seen in the XRD pattern, it has 3 extra peaks, which means the existence of the intermediate phase. After growing the crystal, we can get a fully synthesis crystal like this. In this sample, the XT pattern is clear and is nearly the same as the reference one. So, as a summary, we can get through the design of experiment methodology, we can clarify that the starting material weight, rotational speed, and the MSO usage can significantly influence the crystal size. In addition, we found the capability synthesis procedure, the mechanical formation of capability from the copper nitrate, HBTC, and DMSO occur through the formation of an intermediate phase. In addition, the hydrogen storage shows the capability with the largest crystal size, synthesized with the reduced energy consumption and cost, exhibit the larger hydrogen storage, and is comparable to the hydrogen uptake observed in subthermal capability. At last, I want to thank you, the energy submit, to give me the chance to present my work. If you have any question, please send me the email. And also thank you, my professor, Dr. Meeting, to help me, and the Royal Society China Scholarship Foundation. Thank you for listening.
Thank you, Qian, for a wonderful presentation. Please join all of us.
Thank you.
Hello, Sarvesh, is it audible?